loading dock below all of the buildings. This is what the deck looks like, and then when you walk, it's dizzy. It's an experience. You don't know what's underneath. The latest one, of course, those were all the projects we did as Krawinkler Luth and Associates. We're now operating as Krawinkler Luth and Associates. Helmut had to take his money out to build his son's house. But Helmut remains involved, and Helmut's the only person in the world that I trust implicitly, and when Helmut says something, I believe it and I do it. We got started on a project for the USC School Cinema. It was funded by George Lucas, and the requirement of the project was that we do it as a BIM project, building information model, three-dimensional modeling, but I wanted to do something that was significant structurally, so I talked to Helmut. We had a bourbon, which, by the way, we've probably gone through several barrels over the years since 74. And anyway, over a bourbon, Helmut told me that the wave of the future will be not only performance-based design, but repairable design and controlling non-structural damage. And I said, okay, give me another bourbon, tell me how to do it. And you know, we had a conversation on concepts. We came up with a concept which is a rocking wall, captive between two steel columns, connected to the columns with a slit shear plate. It's capable of absorbing as much energy as we need, and it is capable of going to the deformation we need. Pinned at the base with a rocker that's at the center of the panel, such that the panel itself will translate at the center line at each floor, connected to those floors with a pin at each floor. Here's what the rocker looks like. Those are 1.5-inch plates. This plate, the lug that connects them together, is 2.5 inches wide, or 5 inches this way, 2.5 inches thick, extending up and down a foot. The plate itself, we replaced the studs with rebar hoops going back up into the wall. Let's see, I don't have the rocker drawn here. There's a slit shear plate. The slit shear plate ended up being actually 17 different geometries before we were done. Hampton, you'll be happy to know that LA approved this based on standard practice. They asked if we could design this based on elastic standard equations. We said we could. All we had to do was match the elastic force distribution with plastic force distribution and still protect these concrete panels, which are intended to remain elastic in an earthquake. This is a test we did on one of our panels. We didn't do it. Stanford did it. It was part of a joint program with Illinois, and who else? With Greg Deerline. And we supplied the material as part of the test, and we supplied some geometry that we had worked out, and it got put into the Stanford test. This is what our exterior walls look like. We prefabricated all the rebar, flew it in. Those panels took about 15 minutes a piece to put in. This is what the finished product looks like. The slit shear plate is attached on the inside of the wall, so it's available for inspection and for replacement after an earthquake. Here's Helmut out inspecting the structure, and we get a kick out of having Helmut come out and look at our project. It's a trip to walk around the project with Helmut and have him, at this stage in the project, grill you the way he did about your dissertation. Of course, at this point, it's kind of hard to do anything about it. We did some studies on the slit shear plates. We ended up doing some tweaking of the geometry to get the stress distribution on these blades to be identical. This is one of our, this is the geometry that we developed that was designed to yield in shear at the same time as it yielded in bending. Seemed to work really well. Here's what it looked like, the shear yielding in the middle. And first was a shear yielding, then was a bending yielding in the middle of the blade, and eventually the entire thing plastified. This is a typical hysteresis. Here's Helmut doing what he loves to do, testing. And this is what that specimen looked like. This one went to 3.7 inches. The length of that blade is 9 inches, so if you work that out, that's a distortion in the neighborhood of 40%. And we were, the 18.5% is based on center line to center line of the bolts, not the free span of the blade. Our design deformation in these plates is 3/4 of an inch. We took this as evidence Helmut continues to guide us